conversation. So thanks.
Thank you very much. I would like to thank Tom for this amazing meeting and for this opportunity to speak. I am an optimizer, but I became fascinated with random matrix theory. With the thought of trying to apply it to optimization and improving the scalability of optimization algorithms. So the work I will talk about today is with my PhD student, Zhen Shao, who has recently finished and, well, it's finishing now really. And Jan Fiala, our collaborator at NAG, and Yari Fox, who has been my postdoctoral researcher and is now at Rutherford Appleton Laboratory. So, so I want to start with talking about sketching. So I really liked how one of the first talks yesterday was giving like 5 lessons in random matrix theory. I would like to start with something like that, just a reminder of some things you may know, or in other words, something that has really interested me that we started to look at with Zhen Shao, namely sketching. And after that, I will talk about sparse sketching and some results we have there, and how to then apply them to optimization, to linear least squares, improving the solution of linear least squares, and then to more general non-convex optimization and to subspace methods. So let us begin. So you may be familiar with Johnson-Lindström's lemma, where it all starts. So we have a vector, a given vector in n dimensions, and we apply, as we project it, we project this given vector from the large dimensional n to the small dimensional m. And the matrix S throughout this talk will be an underdetermined matrix. So we can do that while preserving distances. So indeed, if S is a scaled Gaussian and we have a certain that's sufficiently large in its small dimension here, then S will project X correctly into the smaller dimensional Rm while preserving its length with exponentially high probability. This is an exponentially high probability result because here we have a log of the delta, so we could replace that by some value, and then here we would get an exponential. So notice that here we have this dimension of m that depends on the probability of success and the accuracy epsilon s. How can we understand this result? Well, just to give you an intuition, indeed it's a concentration of measured phenomena. If x was random and we measured the length, the relative length of s applied to x, we would get indeed something that concentrates around 1. Now, if x is deterministic, we can think of a Gaussian matrix as being both a transformation, a randomization of x, and a projection. Namely, it's a random projection. So it samples it, it transforms it, it randomizes it, and it samples it. So it gives us a random projection. Now, let's look a little bit more at this dimension, small dimension m, because this is what will really matter to us. How much can we reduce the dimension of n? Well, notice that in here, m does not depend on n. So it does not depend at all on the ambient dimension, which is very good news for us, and neither does epsilon s. Okay, so this is very good, but what happens if we are not trying to project just one given vector or finitely many given vectors, but a whole subspace, so infinitely many points? So consider now a matrix A that's n times d, so it's overdetermined, and we want to project correctly the vectors in the column space of A. So then the dimension of the subspace comes in. So D, or the rank of R, comes in here. So M is now proportional to D, okay? But otherwise, these dependencies stay the same. And still, this M does not depend on the large dimension N. And is this tight? Well, numerically, this plot here at the bottom illustrates this fact that, that if M is less than D, this is a relative residual on the vertical axis of SAY over norm of AY. So you can see that it's not recovered correctly. It's not recovered correctly if M is less than D. However, as soon as it's close to D, we start to get this preservation of distances. However, in all this framework, so either for subspace embeddings here, or in just finitely many point embeddings, we have that S is a scaled Gaussian. And so to form S times A, we get back N. So we don't like that. We don't like that N comes back because S, of course, is a dense matrix. So do we have sparse embeddings? Of course. The simplest is given A, you can uniformly sample rows of A. So in this uniform sampling approach, it works, but you may miss some important information. If A has one row that's that's quite different than the others, and you miss it, then you will fail in your projection, in projecting correctly pairs-wise distances. So when does uniform sampling succeed? When A has low coherence. This low coherence notion is not the same as coherence in compressed sensing or signal processing. It's kind of a different, it's same name, but different concept. But it's to do with leverage scores. So it is really a measure of how similar the rows of A are. To be precise, if you have the SVD of A, then the leverage score is the maximum of the row norms of U. And it's trying to account for this dissimilarity or of the rows. So if so S is a matrix and M dependent coherence is now depends on the coherence of A and D log D, then we can get a subspace embedding with uniform sampling. So these are known results, and the question is, are there better sparse random projections than uniform sampling? Yes, and one of them is hashing. So in sampling matrices, we have one non-zero per row, but in hashing, we have one non-zero per column with random signs. This simple change allows us that when we form S times A, we will touch all the rows in A. And so this is a more robust random projector. In practice, people have noticed that hashing performs similarly to Gaussians. I mean, it's a really good random projector. However, the theoretical results for this have been, for example, from Meng and Mahoney, for any given matrix A, if you choose this one hashing matrix, if M is proportional to D squared, then you can guarantee an oblivious subspace embedding. So distributionally, every matrix in this distribution will give a subspace embedding for the column space of A. If we are willing to restrict the coherence of A, we can improve on the D squared dependence here. Remember, the Gaussian was with D. And indeed, Jean Bourgain showed that if mu is less than or equal to 1 over log D, then S with M proportional to D log squared gives an oblivious subspace embedding. We were further able to improve on that in M, but at the expense of worsening the coherence requirement. So if the coherence is less than 1 over D, then we are able to get M here to be proportional to D, as in the Gaussian case. So we were quite happy about that, though we believe that the coherence requirement of 1 over D could possibly be improved. So hopefully maybe somebody could improve that, but we are happy to see here an M proportional to D dependence. So this is better than sampling. In all these results, D in size of M could be replaced by the rank of R. So it's really a dependence on the rank of A, sorry, on the rank R of A. Can we do better than just with hashing? Well, what if we have more than one non-zero per column? So then we have these S hashing ensembles, and there we were, I mean, this result is known. We just gave, this kind of result is known. We just gave a new proof given our new result for one hashing matrices. So in S hashing matrices, you have this S non-zero per column, and without replacement. And what you have is that if mu is less than whatever we had there before, so like a multiple of 1 over D times square root of S, then S hashing with M proportional to D will be a subspace embedding. So the coherence requirement loosens by square root of S, which is not a huge amount, but it's a constant factor there that you can increase the class of matrices to which you can apply this. We also proposed another kind of ensemble here, and another kind of result, related result to this square root of S improvement. Namely, let's consider a different hashing variant, S hashing variant, in which we choose the number of non-zeros per column with replacement. So we may have them on into the places may repeat. And in that case, we could show the following result. Whatever guarantee you have for one hashing in terms of providing a subspace embedding, you can repeat that for S hashing with an improvement of square root of S in the weakening of the coherence requirement. So whatever A with a coherence of, say, mu bar, you can recover with one hashing. Whatever guarantee you have for that, for one hashing, you can translate that automatically to this S hashing variant for a larger class of matrices multiplied by, with their coherence multiplied by square root of S. And the argument in this result is to do with what happens when you sketch with an S hashing variant. So if you have a U matrix from your SVD of A, sketching A is the same as sketching U from the left. And so when you apply U, so every row gets appears into 3 rows in SU. And what we can do is to draw an analogy between that, what happens there, with considering a different U that repeats the original U 3 times, and then applying a one hashing matrix to that, a one hashing sketching to that. So we can draw this kind of analogy that allows us to get this kind of general result. The third result I would like to mention here is that when we started to think about to look at various random ensembles, we saw that in codes, for example, in Blendenpik that I will talk about in a moment, so in codes that use sketching, people are using this subsampled Hadamard transform. So there are these coherence reducing transformations that people are using, and that they are used by subsampling various rows in those transformations. And what we proposed is to actually replace the subsampling there, because we saw that subsampling is not a good random projector, really, in terms of its subspace embedding properties, is not as good as hashing, to replace that with hashing. And we found this to work very well in practice, as I will say in a moment. And also in theory, we could then give the following result. That's again, because of our one hashing and S hashing results, we can then say that if you have this kind of hashed randomized Hadamard transforms, where the small size of S is proportional to D, and N is proportional to D to power 3, then you can achieve an oblivious subspace embeddings with this. So again, this improves on existing results because of this optimal dependence on D here. Now, numerically, if you, in this plot, I illustrate the benefits of doing hashed coherence reducing transformations compared to subsampled. So here on the horizontal axis, again, we have M proportional to D. And here we have the condition number of a preconditioned given matrix A, preconditioned by doing, you take the S, you sketch A, so you form S times A, you calculate QR for that, and you take R and use it as a preconditioner for A. And if you look at the condition number of the preconditioned system, you can see here in blue is the hashed one. So exactly in the regime where you care about, because you do want to choose numerically M close to D, the condition number of this will be much better than if you did subsampling. So we were encouraged about this, and we used this in a code that I will talk to you about in a moment. Okay, so now, so that's kind of my introduction to sketching and kind of some of our results there for sparse matrices. So we've seen that Gaussian matrices have the optimal random projection properties, subspace embedding properties, and hashing has can have similar in terms of the dimension of the how much the dimension can be reduced, and we saw that subsampling is not so great. So how could we apply this to improve the scalability of optimization algorithms? I want to start first by just the most straightforward application, linear least squares. So here you would sketch both A and B. That would be the standard thing to do. And then you would kind of get rid of your N dependence. But the gold standard here of applying sketching to linear least squares is Blendenpik. So let me tell you a little bit what Blendenpik does, and I already mentioned it a little bit when I mentioned the preconditioner. Instead of just sketching and solving these sketch linear least squares, you can do something much better. You draw S, you form S times A, and you just use the sketching for preconditioning. So in Blendenpik, you QR S times A, and then use R to precondition your matrix A and solve with an iterative method like LSQR. You solve these reduced linear least squares. This approach, tries to solve this linear least squares as exactly as possible. If you do just plain vanilla sketching, when you have a non-zero residual problem, you will not be able to get a very high accuracy solution. But with Blendenpik, like ideas, this is possible. So there are theoretical guarantees from Blendenpik, and there is another code, LSRN. So in Blendenpik, there is it solves dense problems. It does subsampler randomized Hadamard. LSRN tries to do sparse Gaussian, applies sparse Gaussian for the choice of S, and then instead of QR does SVD. And LSRN was very much meant for parallelization of Blendenpik, as well as dealing with sparse, and dealing with rank deficient problems, because Blendenpik cannot deal with rank deficient problems. We have our own implementation skills, and what we try to do in skills, it's a very general code. It can take both dense and sparse linear least squares, so A can be dense or sparse, and it then proceeds with different approaches depending on the on that. For dense problems, it does this hashed randomized DHT, as I mentioned before, instead of subsampled. And we want to be able to deal with rank efficient input. So so when we QR A, we do a randomized column pivoted QR. It's a code of Martinson. For sparse problems, we use S-hashing with 2 non-zeros per column. And then what we do for QR, we use sparse QR. So what we try to do in skills is to take kind of what we best know in NLA that works very well, and also with kind of the best things that we know from sketching. The code still uses LSQR. We've also tried LSMR. The code is available. So the improvements are that it can do ranked efficient problems. It still does QR, which is cheaper than SVD. It can tackle sparse linear squares with targeted methods. And here are some results. On the left-hand side plots here, we just generate sparse random problems for the choice of A, with different coherence for A. And in red is our solver throughout. We compared with LSRN in purple. This is time performance, and also with HSL. I don't know if you're familiar. HSL is like one of the standard numerical linear algebra libraries. They have some state-of-the-art iterative solvers for linear least squares. And with SPQR, this sparse factorization. And we can see in red our solver, it does really well on time for all methods of input, I mean, coherent or incoherent. And then we said, well, let's do what people do in numerical linear algebra. When they test the linearly square solver, they test for sparse problems, they test it on the sparse Florida matrix collection, the standard test set. And here are performance profiles that show you with the proportion of problems solved by a given solver within a certain time budget. So the higher the curve, the better. And again, in red is our solver. And what we found here, so again, we tried to be very fair, and we compared with the state of the art that we found for solvers. And what we found is maybe not dissimilar to what people have seen for Blendenpik, namely that when the problem is very overdetermined, like n is greater than 30 times d, or very ill-conditioned, then this kind of sketching-based, our skill solver, a sketching-based solver really is able to win over the state-of-the-art. When the problems are reasonably well-conditioned, or the ratio of overdeterminants is not so high, these things get closer with the HSL solver that does an incomplete LU, and then I think LSQR, I think. So the incomplete factorization really saves it on time. And I can tell you more about that if you want towards the end. Okay, so now I want to go from this more straightforward application of sketching properties, where I hope I convinced you that what we found in theory that works, we try to use numerically, and we also found it works. I want to step back for a moment and think, how could I take these ideas further to nonlinear optimization? So let me just put things in a context. Let's take, we can take things in two ways. We can sketch in the observational domain, or we can sketch in the variable domain. So let me explain. So let me take the typical sum of functions that I have to solve, for example, when I train a deep net. What is used, let me try first to convince you that sketching is already used there, with SK being a sampling matrix. So let's take our sum of functions, and for each function in the sum of functions corresponds to a data point or an observation. Okay, this would be, for example, in machine learning, in training, or it would be also in least squares, regression problems. And what we do is in machine learning, we say, let's subsample the sum of functions. So let's think of this vector of functions corresponding to each data point. If we apply a sampling matrix to this vector, so we form Sk applied to this vector that contains all these functions Fi, then I get a reduced objective, and I can interpret stochastic gradient as taking a gradient step exactly for this reduced objective. So stochastic gradient, whenever you apply it to a sum of functions, all it does is saying, look, let me sketch in the observational domain. Let me sketch in the data, and then for the sketch problem, let me take a gradient step. So that's the connection there. Maybe it's obvious to you, and I apologize if it's obvious, but I think it's good to kind of think in this framework about it. So one way is to apply it there. And in fact, in what I told you earlier, I was kind of doing that for linear least squares. I was sketching from the left. I was sketching in my data. We can also do another thing, which is to sketch in the variables. So I can take my vector x, and again, Sk is a sampling matrix. So when I take Sk transpose applied to reduced vector y, so I let x be replaced by this Sk transpose y. If Sk is a sampling matrix, then this is nothing but a block of my variables. So I randomly select a subset of my variables. So it's nothing but randomized block coordinate methods. So when Sk is a sampling matrix, I can sketch in the observational domain to get, say, stochastic gradient like ideas, or I can sketch in the variable domain and I get randomized block coordinates. However, we just saw at the start of this talk that sampling is not a good random projector. So can we do better? Can we use some of these better random projectors and get better methods? Because for block coordinates, for example, you can prove convergence for fixed block size with positive probability of an algorithm when you try to minimize a non-convex function. But could we get a better guarantee? And for the remainder of my talk, I would like to tell you about some of those ideas. So how to improve on doing random subspace methods for finding, local optimization, finding, minimizing a non-convex, a potentially non-convex function f, where f is smooth, and applying a random subspace method. So how could I be doing that? So in non-convex optimization, at every step, we approximate our nonlinear function f. At the current iterate, we have some point xk. That's the best point found so far, let's say. And we approximate it by a simpler model. And then we minimize this model to find a change in the variables. So it can be, if it's a first order model, then you get a gradient descent-like method. If it's a second order model, you can get more like a Newton-like direction. So this is the full dimensional approach. So I have iterates xk, and then I just compute changes to these iterates xk. Now what I want to do is that at every iteration, though every iterate xk is in the full dimensional space, what I want is that this local model is in a random subspace. So at every iterate xk, I draw a random subspace. So I choose Sk to be a sketching matrix, m times n, so still underdetermined. And then I look at forming a model in the subspace. So I compute the change to my iterates as hat in a reduced subspace Rm. And when I replace my S by this Sk transpose S hat, so I replace it in here, I get here a projected gradient in the subspace and a projected or reduced second derivative or approximate second derivative like matrix. So what I get, of course, I get a smaller dimensional model. That's good. So I have to solve a smaller dimensional problem. But I want you to note that I'm projecting the gradient. So for example, if Sk is a sampling matrix, this would mean that I just compute some of the gradient entries, not all of them, or I just compute some projection of it. So I don't need to know the true full gradient for this. I just need to know its projection in the subspace. So reduced cost of derivatives as well as model minimization. And to get a convergent method, you need to then do something more, not just minimize this model in the subspace. You need to measure if you progressed in your function when you minimized your subspace model. And if that's the case, then you can accept your point that you calculated in the subspace and then draw another subspace and continue. Or you may say, well, I think that I did not decrease the function enough, and then you can stay at the same point and change your line search or change your trust region. So you can adjust some algorithm parameters, standard ones, line search, trust region, or regularization, to make sure that you can decrease the function when you accept your points eventually. So I'm taking the standard framework of non-convex algorithms for non-convex optimization, can be anything, trust region, line search, regularization. And in there, what I'm saying is I want to just calculate a reduced subspace model that I calculate by drawing random subspaces. So I draw a random subspace, I compute a model, and keep doing that. So under what conditions can I guarantee convergence here? Well, the sketching accuracy has to capture correctly just the length of the sketch gradient. And this is one of the things that we most were happy about, that we got a very weak condition under which we can show very strong convergence properties. So if the projected gradient is at least a multiple of the true gradient with some probability, then we can say that this kind of random subspace trust region or line search or regularization framework will have almost sure convergence. And moreover, we can quantify its global rate of convergence. Indeed, we have here that n is at most a multiple of 1 over epsilon squared. And in terms of iterations, to generate a true gradient below epsilon. And this holds at least with exponentially high probability. And 1 over epsilon squared is exactly the deterministic complexity of this kind of methods if I didn't use a subspace and I just used full models. These algorithms are adaptive. You have to be careful how fast or how slow you change your line search. Of course, if you want to assume you know the Lipschitz constant and choose some ideal line search, okay, you can do that, and then you have less problems. But I'm trying to have a practical method, and so I allow adaptive parameters. But these adaptive parameters actually help you if you don't decrease them too fast when you have unsuccessful steps where you can't make progress, and you're careful with how you make those choices, you can ensure almost sure convergence. So this was the condition I had on my sketching accuracy. If I look at it, it reminds me of one thing: embeddings, random embeddings. All I'm requiring for the convergence of my method is to embed correctly one vector. So if you remember the sketching results I started with, I can do that if m is proportional here to log of the failure probability times epsilon minus 2. But this epsilon here is this epsilon here. It's not the epsilon, the accuracy on my small gradient that I'm trying to achieve with my algorithm. And so it can be anything like a half. So essentially, this framework allows me to have random subspace variants with almost sure convergence of classical optimization algorithms, where the subspace dimension is fixed and it can be small. This is also true for S-hashing. And so I can achieve these properties from this. I can apply sketching properties here to ensure this condition. However, we can immediately see that if SK is a sampling matrix, so in the case of block coordinate methods, I cannot secure this condition for any m. Because remember, sampling was very dependent on the coherence. In the size of m, the coherence was coming in. And what this happens when you have one vector, you have a coherence dependent condition there. In particular, you have to require that the gradient vector has similar components, similar in magnitude components. And then you can guarantee almost sure convergence of block coordinate descent, which accords with our intuition and our experience that block coordinate methods often you may miss some important components. If one of the components in the gradient vector is very important and you keep missing it when you choose your random block, then you may have a problem. I don't have much time left. The proof of our result here for random subspace methods relies on probabilistic model theory. So it uses some of the ingredients from there, which is a framework that says that what you try to have is a model of your objective at the current point that's good, sufficiently close to, say, a Taylor model with some probability, but it can be arbitrarily bad otherwise. And in that framework, you adapt your algorithm parameters and they help you get out of problematic situations, and they help you also control the convergence. But our conditions here are much weaker than what probabilistic model theory requires. In probabilistic model theory, you have to have agreement between the gradient entries and your approximate gradient and your true gradient. Their entries have to be, you have to have a condition on those, on that error, on component-wise error, while here we just require a lower bound on the length of the projected gradient. Okay, I don't have time to go into this. I was going to show you that with these ideas I just presented, you can immediately apply it, for example, to nonlinear least squares and get block coordinate or random subspace Gauss-Newton-like methods. So though what I talked about looked in some way like a first order framework, in fact, you can use it to sketch the Jacobian in nonlinear regression problems. So to get a variant where what you're sketching is the first order matrix of derivatives, the derivatives of your error function R, this vector function R. That framework, for example, I've already used it for example, in climate modeling. It was very, very beneficial to be able to do something like this. And if you want to ask me at the end, I can tell you a bit more. We've also tried some of these ideas on some loss functions when you try to do some training, some classification or in some given data set. And I can illustrate some of the key ideas here, that if you look at the iterations of a method, of these methods, so if you have a method that takes the full gradient, full Jacobian, so here it's full Jacobian, full gradient for Gauss-Newton, then in terms of the iteration of the method, you get, and here we have the iterations versus objective decrease, you get, very few iterations of a full model method. And then the block coordinate methods, random subspace methods, they will of course take more iterations. But when you look at runtime, then to run a small number of iterations of a full model method takes much longer than doing some of these random subspace of block coordinates methods. And similarly, for how many entries, how many columns of your Jacobian, how many finite differences do you need to calculate an approximate Jacobian? Okay, I'm going to wrap up. One of the classes of methods that is very much affected by scalability issues is derivative-free optimization. And we have already extended this framework that I've just talked about of random subspace to improving the scalability of derivative-free, where we use the sketching for constructing the interpolation model. So it's a bit different than what I said here, but it's similar ideas. There are many papers that talk about sketching in the observational domain. excuse me. So I don't have a lot of time to talk about that here. For example, Courtney has done some work on that. And another direction related to this, because there is another class of problems that we are very worried about scalability for, is global optimization. Global optimization algorithms are notoriously poorly scalable, far worse than everything I've talked about today. There we have a different kind of approach, also using sketching, for sketching in the subspace domain. Thank you very much for your attention.